Hello aspirants, welcome to Magic World of Physics. In this video, we are going to discuss about some questions from nuclear physics which is asked in various exams like LATE, barc, just differ. Hope this video will be helpful for your coming barc exam 2026. Without any further delay, let's get started. The first question is, the radius of a 29 Cu64 nucleus is measured to be 4.8 into 10 power minus 13 centimeter. The radius of a 12 Mg27 nucleus can be estimated to be dash. So since r is equal to r0 a raised to 1 by 3, we can write r mg by rcu is equal to a mg by acu the whole raised to 1 by 3. This is equal to 27 by 64 the whole raised to 1 by 3. So we can write r mg by rcu is equal to 3 by 4. That is r mg is equal to 3 by 4 into 4.8 into 10 power minus 13. This is equal to 3.6 into 10 power minus 13 centimeter. So this is the answer. The next question is, the intrinsic electric dipole moment of a nucleus ZXA is dash. We know that the intrinsic dipole moment of a nucleus is always zero. This is because the nucleus is composed of neutrons and protons, and a strong nuclear force that binds them together is charge independent, and it doesn't create an inherent separation of positive and negative charges that would lead to a permanent dipole moment. So the dipole moment is zero, and we need to understand that the electric dipole moment is arising due to the separation of positive and negative charges within the system, and due to this nuclear force and the spherical symmetry of most nucleus, the center of mass of nucleus coincides with the center of charge. That is, the positive and negative charges are essentially at the same point. So there is no separation of charge and there is no dipole moment. So that the answer is 0. The next question is, the radius in the Coulomb energy between the mirror nuclei 24 Cr49 and 25 Mn49 is 6 MeV. Assuming that the nuclei have a spherically symmetric charge distribution, that T square by 4 pi epsilon 0 is approximately 1 MeV femtometer, then what is the radius of 25 Mn49 nucleus? So here delta EC, that is the Coulombic energy, is 6 MeV, and we know that delta EC is equal to E square by 4 pi epsilon 0 into 3 into Z1 square minus Z2 square by 5R. And here it is given that E square by 4 pi epsilon 0 is 1 MeV femtometer. So we can write 6 MeV is equal to 1 MeV femtometer into 3 by 5R into Z1 square minus Z2 square. That is, R is equal to 1 femtometer divided by 6 into 3 by 5 into 25 square minus 24 square. This is equal to 4.9 into 10 raised to minus 15 meter. The next question is, the root mean square energy of a nucleon in the nucleus of atomic number A in its ground state varies as dash. So here we need to find a relationship between E and A. We know that delta E is equal to delta P square by 2m. This is equation number 1. And we know by uncertainty principle, delta P is equal to h cut by delta x. And delta x is equal to 2r, because this is the uncertainty in the position of that nucleus. So we can write delta P is equal to h cut by 2r. This is equation number 2. Substituting the value of 2 in 1, we can write delta E is equal to h cut square by 8r square m, where r is equal to r0 a raised to 1 by 3. We can write it as, this is equal to h cut square by 8r0 square a raised to 2 by 3 into m. That is, delta E is proportional to a raised to minus 2 by 3. So this is the answer. Next question is, let ES denote the contribution of a surface energy per nucleon in the liquid drop model. The ratio ES of 13Al27 is to ES of 30Zn64 is dash. We know surface energy is minus AS into a raised to 2 by 3. Let it be ES dash. Then we know that surface energy per nucleon ES is equal to ES dash by A. That is equal to AS a raised to 2 by 3 divided by A. That is equal to a raised to minus 1 by 3 into AS. That is, ES is proportional to a raised to minus 1 by 3. So we can write ES of AL divided by ES of Zn is equal to 27 by 64 the whole raised to minus 1 by 3. This is equal to 64 by 27 the whole raised to 1 by 3. That is 4 cube by 3 cube the whole raised to 1 by 3. This is equal to 4 by 3. That is the ratio is 4 is to 3. The next question is the binding energy of a light nucleus in MeV is given by approximate formula BAZ is equal to 16A minus 20A raised to 2 by 3 minus 3 by 4 Z square A raised to minus 1 by 3 plus 30 N minus Z the whole square by A, where N is the equal to A minus Z, that is the neutron number. The value of Z of the most stable isobar for a given A is dash. We know that B of A is equal to 16A minus 20A raised to 2 by 3 minus 3 by 4 Z square A raised to minus 1 by 3 plus 30 N minus Z the whole square by A. And we know N is equal to A minus Z. So we can rewrite it as B of A is equal to 16A minus 20A raised to 2 by 3 minus 3 by 4 Z square A raised to minus 1 by 3 plus 30 into A minus 2Z the whole square by A. So dB by dz is equal to minus 3 by 4 into a raised to minus 1 by 3 into 2z plus 30 by a into 2 into a minus 2z into minus 2. That is, here for most stable nucleus dB by dz is 0. So we can write 0 is equal to minus 3 by 2 z a raised to minus 1 by 3 minus 120 divided by a into a minus 2z. Multiplying with a, we get minus 3 by 2 is a raised to 2 by 3 minus 120 into a minus 2 is equal to 0. That is minus 3 by 2 is a raised to 2 by 3 minus 120 a plus 240 z is equal to 0. That is Z into 240 minus 3 by 2 a raised to 2 by 3 is equal to 120a. That is Z is equal to 120a divided by 240 minus 3 by 2 into a raised to 2 by 3. This is equal to 240a divided by 480 minus 3a raised to 2 by 3, and this is equal to 80a divided by 160 minus a raised to 2 by 3. That is Z is equal to a divided by 2 minus a raised to 2 by 3 by 80. That is equal to a divided by 2 into 1 minus a raised to 2 by 3 by 160. That is equal to a by 2 into 1 minus a raised to 2 by 3 by 160 the whole raised to minus 1. So this is the answer. The next question is, if the binding energy B of a nucleus is given by B is equal to AVA minus AS a raised to 2 by 3 minus A asymmetric 2z minus a the whole square by a plus ac z square by a raised to 1 by 3, where AV is 16 MeV, AS is equal to 16 MeV, A asymmetric is equal to 24 MeV, and AC is equal to 0.75 MeV. Then for the most stable isobar for a nucleus with A is equal to 216 is dash. Here we need to find the value of Z for a most stable nucleus. That is, Z0 is equal to A divided by 2 plus AC divided by 2 AA into A raised to 2 by 3. Here A is equal to 216. So this is equal to 216 divided by 2 plus 0.75 divided by 2 into 24 into 216 the whole raised to 2 by 3. Solving this, we get the answer as 84. So the answer is 84. The next question is, of the nuclei of mass number A is equal to 125, the binding energy calculated from the liquid drop model, given that the coefficient for the Coulomb and asymmetric energy are AC is equal to 0.7 MeV and A asymmetric is equal to 22.5 MeV respectively, is a maximum for dash. Here also it is asking about the Z value for the most stable nucleus. That is, Z0 is equal to A divided by 2 plus AC by 2 AA into A raised to 2 by 3. This is equal to 125 divided by 2 plus 0.7 divided by 2 into 22.5 into 125 the whole raised to 2 by 3. So this is equal to 52.32. So we should select the option which has the Z value as 52. So the answer is 52 TE 125. Next question is, the physical formula for the binding energy of a nucleus of atomic number Z and mass number A is 15.8a minus 18.3a raised to 2 by 3 minus 0.714 z into z minus 1 divided by a raised to 1 by 3 minus 23.2 into a minus 2z the whole square by a. The ratio of z by a for the most stable isobar of a is equal to 64 nucleus is nearest to dash. We know that binding energy is equal to AVA minus AS a raised to 2 by 3 minus AC Z square by a raised to 1 by 3 minus AA into a minus 2Z the whole square by a plus or minus delta by a raised to 3 by 4. This is equation number 1. And here it is given that BE is equal to 15.8A minus 18.3A raised to 2 by 3 minus 0.714 Z into Z minus 1 divided by a raised to 1 by 3 minus 23.2 into a minus 2Z the whole square by a. This is equation number 2. This equation 1 and 2 implies AV is equal to 15.8, AS is equal to 18.3, AC is equal to 0.714, AA is equal to 23.2. Then for the most stable nucleus, Z0 is equal to A divided by 2 plus AC divided by 2 AA into a raised to 2 by 3. That is Z0 by A is equal to 1 by 2 plus AC by 2 AA into a raised to 2 by 3. This is equal to 1 divided by 2 plus 0.714 divided by 2 into 23.2 into 64 the whole raised to 2 by 3. This is equal to 0.45. The next question is the binding energy B of a nucleus is approximated by the formula B is equal to A1A minus A2 a raised to 2 by 3 minus A3 Z square a raised to minus 1 by 3 minus A4 into A minus 2Z the whole square a raised to minus 1, where Z is the atomic number, A is the mass number of the nucleus. If A4 by A3 is approximately 30, then the atomic number is set for a naturally stable isobars. Constant value of A is dash. So here it is given that B is equal to A1A minus A2 a raised to 2 by 3 minus A3 Z square a raised to minus 1 by 3 minus A4 into A minus 2Z the whole square a raised to minus 1. For most stable isobar, dou B by dou Z should be 0. That is minus A3 into 2Z divided by a raised to 1 by 3 minus A4 into 2 into A minus 2Z into minus 2 by A is equal to 0. That is A3 into Z divided by a raised to 1 by 3 is equal to 2A4 A by A minus 4A4 Z by A. That is Z by A into A3 into a raised to 2 by 3 plus 4A4 is equal to 2A4. That is Z is equal to 2A4 A divided by A3 a raised to 2 by 3 plus 4A4. That is equal to A divided by 2 plus A3 by 2A4 a raised to 2 by 3. In the question it is given that A4 by A3 is equal to 30. That is A3 by A4 is equal to 1 by 30. That is Z is equal to A divided by 2 plus 1 by 60 into A raised to 2 by 3. This is equal to 60A divided by 120 plus A raised to 2 by 3. So this is the answer. The next question is, let us approximate the nuclear potential in the shell model by a three-dimensional isotropic harmonic oscillator. Since the lowest two energy levels have angular momenta L is equal to 0 and L is equal to 1 respectively, which of the following two nuclei having magic number of protons and neutrons? So here we need to find which options have the magic number of protons and neutrons. We know that the magic numbers are 2, 8, 20, 28, 50, 82, 126. In the option A, it is given that 2He4 and 8O60. For 2He4, N is equal to, that is the number of neutrons is equal to 2 and the number of protons, that is P, is equal to 2. And for 8O16, N is equal to 8 and P is equal to 8. We know that 2 and 8 are magic numbers. So the option A contains the magic number of protons and neutrons. Then coming to option B, 1D2. That is proton is equal to 1 and number of neutrons is equal to 1. Because it is the neutron. D means neutron. So here the number of neutrons and protons is equal to 1. And for 4BE8, neutron is equal to 4 and proton is equal to 4. We know that 1 and 4 is not a magic number. So B is wrong. Then coming to option C, that is 2He4. For 2He4, P is equal to 2 and N is equal to 2. 2 is a magic number. But 4B8, N is equal to 4 and P is equal to 4 and 4 is not a magic number. So that option C is wrong. Then coming to option D, that is 2He4. For 2He4, P is equal to 2 and N is equal to 2 and 2 is a magic number. But 6C12 has P is equal to 6 and N is equal to 6. 6 is not a magic number. So option D is also wrong. So the correct option is option A. The next question is, according to shell model, the parity and the spin of the two nuclei 51Sb125 and 38Sr89 are respectively. So the sequence of energy levels in the order 1s 1 by 2, 2, 1p 3 by 2, 2, 1p 1 by 2, 2, 1d 5 by 2, 6, 2s 1 by 2, 2, 1d 3 by 2, 4, 1f 7 by 2, 8, 2p 3 by 2, 4, 1f 5 by 2, 6, 2p 1 by 2, 2, 1g 9 by 2, 10, 1g 7 by 2, 8. And here for 51 SB 125, we know that Z is equal to 51 and number of neutrons is equal to 74. Here the unpaired number is the proton number, that is Z is equal to 51. So writing the sequence of energy level for this, we can write it as 1s 1 by 2, 2, 1p 3 by 2, 4, 1p 1 by 2, 2, 1d 5 by 2, 6, 2s 1 by 2, 2, 1d 3 by 2, 4, 1f 7 by 2, 8, 2p 3 by 2, 4, 1f 5 by 2, 6, 2p 1 by 2, 2, 1g 9 by 2, 10, 1g 7 by 2, 1. So the unpaired electron is filled in the g orbit. So for g orbit, L is equal to 4 and the last electron is filled in 1g 7 by 2. So that j is equal to 7 by 2. So here the parity is pi is equal to minus 1 the whole raised to L, that is here L is equal to 4, that is minus 1 the whole raised to 4, that is equal to 1. That means here we get the positive parity. So j pi is equal to 7 by 2 plus. Similarly for 38SR89, we know Z is equal to 38 and N is equal to 51. So here the odd number is N is equal to 51. So for N is equal to 51, we can write 1s 1 by 2, 2, 1p 3 by 2, 4, 1p 1 by 2, 2, 1d 5 by 2, 6, 2s 1 by 2, 2, 1d 3 by 2, 4, 1f 7 by 2, 8, 2p 3 by 2, 4, 1f 5 by 2, 6, 2p 1 by 2, 2, 1g 9 by 2, 10, 1g 7 by 2, 1. So here the last electron is filled in the g orbit and have the j value 7 by 2. As it is the g orbit, we can write L is equal to 4. Then the parity is pi is equal to minus 1 the whole raised to L, that is minus 1 the whole raised to 4. This is even parity. So we can write j pi is equal to 7 by 2 plus. So here for both the cases, j pi is equal to 7 by 2 plus. So the answer is option D. The next question is, according to the shell model, the total angular momentum in the units of h cut and the parity of ground state of 3Li7 nucleus is dash. So here Z is equal to 3 and the number of neutrons is equal to 4. So here the odd number is Z. So for Z is equal to 3, we can write the energy sequences as 1s 1 by 2, 2, 1p 3 by 2, 1. That is the last electron is filled in 1p 3 by 2. That is j is equal to 3 by 2 and L is equal to 1. That is here for parity, pi is equal to minus 1 the whole raised to L, that is equal to minus 1 the whole raised to 1, that is equal to minus 1. So we get the answer as 3 by 2 with the negative parity. So here the option A is the answer. The next question is, according to the shell model, the nuclear magnetic moment of the 13Al27 nucleus is given that for a proton, GL is equal to 1 and GS is equal to 5.586, and for a neutron, GL is equal to 0 and GS is equal to minus 3.826. So here for 13Al27, we know Z is equal to 13 and N is equal to 40. So here the odd one is Z is equal to 13. So for Z is equal to 13, we can write 1 as 1 by 2, 2, 1p 3 by 2, 4, 1p 1 by 2, 2, 1d 5 by 2, 5. So here the unpaired electron is filled at 1d 5 by 2. So we can write J is equal to 5 by 2 and L is equal to 2 as it is d orbital. So here the magnetic moment equation can be written as mu is equal to 1 by 2 into 2j minus 1 plus gs into mu 1. Here gs is the spin g factor and it is also given that is equal to 5.586. So we can write mu is equal to half into 2 into 5 by 2 minus 1 plus 5.586 into mu n, that is equal to 4.793 mu n. So this is the answer. The next question is the spin parity assignments for the ground and the first excited state of the isotope 28Ni57 in the single particle shell model are dash. So here for the ground state of 28Ni57, we know that the number of neutrons is equal to 29 and the protons is equal to 28. So here the odd one is n is equal to 29. So for n is equal to 21, we can write 1 as 1 by 2, 2, 1p 3 by 2, 4, 1p 1 by 2, 2, 1d 5 by 2, 6, 2s 1 by 2, 2, 1d 3 by 2, 4, 1f 7 by 2, 8, 2p 3 by 2, 1. So here the last electron is filled in 2p 3 by 2. So here we can write J is equal to 3 by 2 and as it is p, we can write L is equal to 1. And here pi is equal to minus 1 the whole raised to 1, that is equal to minus 1. So the negative parity. So that J pi is equal to 3 by 2 minus. Then for the first excited state, we can write 1 as 1 by 2, 2, 1p 3 by 2, 4, 1p 1 by 2, 2, 1d 5 by 2, 6, 2s 1 by 2, 2, 1d 3 by 2, 4, 1f 7 by 2, 8, 2p 3 by 2, 1. And here the last electron get moved to 1f 5 by 2. So here the last electron is filled in 1f 5 by 2. So here J is equal to 5 by 2 and L is equal to 3. So the J pi is equal to 5 by 2 minus. So this is the answer. So for ground state, J pi is equal to 3 by 2 minus, and for first excited state, J pi is equal to 5 by 2 minus. The next question is the first excited states of rotational spectrum of the nucleus 92 uranium 238 has an energy 45 keV above the ground state. The energy of the second excited state in keV is dash. Here we know that Ej is equal to h cut square by 2i into j plus 1. This is equation number 1. And here j is equal to 0 plus 2 plus 4 plus 6 plus etc. For ground state, j is equal to 0 plus. That is E is equal to 0 keV. And for the first excited state, J is equal to 2 plus, and it is given that here E is equal to 45 keV. Then the first equation implies 45 keV is equal to h cut square by 2i into 2 into 3. By substituting the value of J, we get like this. That is h cut square by 2i, which is equal to 45 by 6 into keV. This is equation number 2. Then for second excited state, we know J is equal to 4 plus. That is E2 is equal to h cut square by 2i into 4 into 5. That is 20 h cut square by 2i. This is equal to h cut square by 2i is equal to E2 by 20. This is equation number 3. Comparing equation number 2 and 3, we get 45 by 6 is equal to E2 by 20. That is E2 is equal to 150 keV. So the answer is 150. The next question is the low-lying energy levels due to the vibrational excitations of a even nucleus are shown in the figure below. So here what is the spin parity of the level E1? This is a theoretical question. Here it is mentioned that it is asking about the vibrational excitation. We know that the lowest order vibrational is exhibited by the quadrupole mode. So in the quadrupole oscillation, we know that the energy levels are marked like this. That is 0 plus 2 plus, and in the two phonon quadrupole, the energy levels are marked like 4 plus 2 plus 0 plus. Here we need to find the J pi value of E1, which is 0.56 energy. So here we know that it is the one phonon quadrupole energy level, so that J pi is equal to 2 plus. So here the answer is 2 plus. That is, the parity is positive and the value of J is 2. So the option D is the right answer. Next question is, an excited state of a 4Be8 nucleus decays into 2 alpha particles which are in a spin parity 0 plus state. If the mean lifetime of this decay is 10 power minus 22 seconds, then the spin parity of the excited state of the nucleus is dash. The reaction mentioned in this question is, that is 4Be8 changes to 2 alpha particle, that is 4Be8 changes to 2He4 plus 2He4, and we know that in a nuclear decay spin and parity is conserved. So here we know beryllium is a boson. So for a boson the wave function is symmetric. So here the boson beryllium is converted to alpha particle. So the total wave function of that alpha particle is also symmetric. That is, L must be even. As L is the even parity, we can say that the parity is positive. And as beryllium is an even nuclei, the possible values of J are 0 plus 2 plus 4 plus. So for the excited state, 2 plus is the spin and the parity. So the answer is 2 plus. The next question is, the magnetic moments of the proton and neutron are 2.792 mu n and minus 1.913 mu n, where mu n is the nuclear magnetic moment. The values of the magnetic moments of the mirror nuclei 9F1910 and 10Ne19 respectively in the shell model are closest to dash. So for 9F19, protons is equal to 9 and neutrons is equal to 10. So here the odd number is protons. So that it can be written as 1 as 1 by 2, 2, 1b 3 by 2, 4, 1b 1 by 2, 2, 1d 5 by 2, 1. So the last electron is filled in 1d 5 by 2. So that J is equal to 5 by 2. So J is in the form of J is equal to L plus half. Then only we get 2 plus half, that is equal to 5 by 2. Here L is equal to 2 because the last electron is filled in d orbit. So for d orbit L is equal to 2. So that it is written as 2 plus half, this is equal to 5 by 2. This is equal to 2 by 2.5. So we understood that the J is in the form of L plus half. Then for J is equal to L plus half, we can write nu z of proton is equal to J plus 2.29 into mu n, that is equal to 2.5 plus 2.29 into mu n, that is equal to 4.79 into mu n. Then for 10 Ne19, we know the number of neutrons is equal to 9. This is the odd number, that is it can be written as 1 as 1 by 2, 2, 1b 3 by 2, 4, 1b 1 by 2, 2, 1d 5 by 2, 1. Here also J is equal to 5 by 2 and it is in the form of L plus half. So we can write the mu z of neutron is equal to minus 1.91 mu n. Here none of the options matches with the answer, but the most appropriate answer that is closest to our answer is option D. So the option D is the answer. For this type of question, we need to understand some points. That is, for unpaired proton, if J is equal to L plus half, mu z of P is equal to J plus 2.29275 into mu n. Then for J is equal to L minus half, mu z of proton is equal to J by J plus 1 into J minus 1.29275 into mu n. Then for unpaired neutron, if J is in the form of L plus half, we can write mu z of neutron is equal to minus 1.9135 into mu n. And if J is equal to L minus half, mu z of neutron is equal to 1.9135 into J divided by J plus 1 into mu n. Then the total mu z is equal to mu z of proton plus mu z of neutron. So in this way we can solve each question. Next question is, the reaction 1D2 plus 1D2 gives 2He4 plus pi 0 cannot proceed via strong interactions because it violates the conservation of dash. So here we need to check in this reaction which term is not conserved. So we know that the deuteron contains 1 protons and 1 neutrons. That is, the baryon number is 2. Then for helium, proton is 2 and neutron number is 2. That is, the baryon number is 4. So here the reaction is 1d2 plus 1d2 gives 2He4 plus pi 0. The baryon numbers are 2, 2, 4, 0 respectively. So here we understood that the left hand side and the right hand side baryon number is equal. That is, the baryon number is conserved here. Then the value of isospin, that is I. Here the values of I are 0, 0, 0, 1 respectively. That is, the value of I is not conserved because the LHS we get the value 0 and in RHS we get the value 1. So that I is not conserved. So here B is conserved and I is not conserved. So here the as the atom is neutral, we can also say that the charge is conserved. And the angular momentum is also conserved in nuclear reaction. So we can say that the only term that is not conserved here is the isospin. So the answer is isospin. The next question is, the strong nuclear force between a neutron and a proton in a zero orbital angular momentum state is denoted by FMPR, where R is a separation between them. Similarly, FNN of R and FPP of R denotes the forces between a pair of neutrons and protons, respectively, in the zero orbital momentum state. Which of the following is true on average if the internucleon distance is 0.2 femtometer less than or less than 2 femtometer? Inside the nucleus, the interaction between the neutron-neutron and neutron-proton is always attractive due to the nuclear force, whereas the force between the proton and proton is repulsive due to the Coulombic repulsion. So we can say that FNN and FNP are always attractive, where FPP is repulsive in nature. The next question is, a radioactive element X decays to Y, which in turn decays to a stable element Z. The decay constant from X to Y is lambda 1 and that from Y to Z is lambda 2. If to begin with there are only N0 atoms of X at short time, where T less than 1 by lambda 1 and T less than 1 by lambda 2, the number of atoms of Z will be dash. Here it is given that X decays to Y with the decay constant lambda 1 and Y decays to Z with the decay constant lambda 2, and that T is equal to 0, the amount of X is N0, Y is 0 and Z is 0, and at after time T, amount of X is N1, amount of Y is N2, and for Z it is N3. Then for Z nuclei, the rate equation is dN1 by dt is equal to minus lambda 1 N1. For Y nuclei, the rate equation is dN2 by dt is equal to lambda 1 N1 minus lambda 2 N2. For Z nuclei, it is dN3 by dt is equal to lambda 2 N2. Solving these equations, we get N1 is equal to N0 e raised to minus lambda 1 t, N2 is equal to lambda 1 N0 divided by lambda 2 minus lambda 1 into e raised to minus lambda 1 t minus e raised to minus lambda 2 t, N3 is equal to N0 into 1 minus lambda 2 by lambda 2 minus lambda 1 into e raised to minus lambda 1 t plus lambda 1 divided by lambda 2 minus lambda 1 e raised to minus lambda 2 t. That is, N3 is equal to N0 into 1 minus lambda 2 divided by lambda 2 minus lambda 1 into 1 minus lambda 1 t plus lambda 1 square t1 square by 2 plus lambda 1 by lambda 2 minus lambda 1 into 1 minus lambda 2 t plus lambda 2 square t square by 2. This is equal to N0 into lambda 1 by lambda 2 minus lambda 1 into lambda 2 square t square by 2 minus lambda 2 by lambda 2 minus lambda 1 into lambda 1 square t square by 2. This is equal to lambda 1 lambda 2 t square by 2 into n0 into lambda 2 by lambda 2 minus lambda 1 minus lambda 1 by lambda 2 minus lambda 1. This is equal to half into lambda 1 lambda 2 n0 t square. So this is the answer. The next question is, the nuclei of 137 Cs decays by the emission of beta particles with an half-life of 30.08 years. The activity in the units of disintegration per seconds or becquerel of a 1 mg source of 137 Cs prepared on January 1, 1980 as measured on January 1, 2021 is closest to dash. So here the activity is equal to lambda n, this is equal to lambda n0 e raised to minus lambda t, this is equation number 1. Lambda is equal to 0.693 by t half, this is equation number 2. Substituting 2 in 1, we get a is equal to 0.693 by t half into n0 into e raised to minus 0.693 by t half into t, this is equation number 3. And we know n0 is equal to mass in grams divided by mass number, that is 137 into 6.02 into 10 power 23, that is equal to 10 power minus 3 divided by 137 into 6.02 into 10 power 23. So here A is equal to, that is activity is equal to 0.693 divided by 30.08 into 10 power minus 3 by 137 into 6.02 into 10 power 23 into e raised to minus 0.693 divided by 30.08 into 40. This is equal to 0.023 into 4.3 into 10 power 18 into 0.3977. This is equal to 0.0393 into 10 power 18 disintegration per year. That is equal to 0.0393 into 10 power 80 divided by 365 into 24 into 60 into 60 disintegration per second. This is equal to 1.24 into 10 power 9 disintegration per second. This is the answer. The next question is, what should be the minimum energy of a photon for it to split an alpha particle at rest into a tritium and a proton? Here the masses of 2He4, 1H3, 1H1 are 4.0026 AMU, 3.0161 AMU and 1.0073 AMU respectively. And here 1 AMU is equal to 938 MeV. So here the reaction given as 2He4 gives 1H3 plus 1H1. So here the Q value is equal to mHe minus m of 1H3 minus m of 1H1 into C square. That is equal to 4.0026 minus 3.0161 minus 1.0073 into 938. That is equal to 19.37 MeV. The next question is, if in a spontaneous alpha decay of 92 U232 at rest, the total energy released in the reaction is Q, then the energy carried by the alpha particle is dash. So the equation is Q is equal to A divided by A minus 4 into K alpha. That is K alpha is equal to A minus 4 by A into Q. That is equal to 232 minus 4 divided by 232 into Q. This is equal to 57 by 58 into Q. So this is the answer. The next question is, the reaction 29Cu63 plus P gives 30 Zn63 plus N is followed by a prompt beta decay of zinc, that is 30 Zn63 gives 29 Cu63 plus E plus nu E. If the maximum energy of the positron is 2.4 MeV, the Q value of the original reaction in MeV is nearest to dash. Here the masses of electron, proton, neutrons are given as 0.5, 938 and 939.5 MeV by C square respectively. In the reaction, 30 Zn63 gives 29 Cu63 plus E plus nu E. We know that the Q value is equal to mZn minus mCu minus me into C square. And mZn is equal to mZn atom minus 30 Me. and MCU is equal to MCU atom minus Z. Here Z is equal to 29, so that minus 29 ME. So Q1 is equal to, that is substituting the value of MZ and MCU in the value of Q value equation, we get Q1 is equal to MZN atom minus 30 ME minus MCU atom minus 29 ME minus ME into C square. That is MZN atom minus 30 ME minus MCU atom plus 29 ME minus ME into C square. That is MZN atom minus MCU atom minus 2 ME into C square. That is MCU atom minus MZN atom is equal to minus Q1 by C square minus 2ME. This is equation number 1. And for the reaction, 29Cu63 plus P gives 30 Zn 63 plus N. We know the Q value, let it be Q2, that is equal to MCU atom minus 29ME plus MP minus MZU atom minus 30ME minus Mn into C square, that is equal to MCU atom minus MZN atom minus 29ME plus 30ME plus MP minus Mn into C square, that is equal to MCU atom minus MZN atom plus Me plus MP minus Mn into C square. This is equation number 2. Substituting the value of 1 into, we get Q2 is equal to minus Q1 by C square minus 2ME plus MP minus Mn into C square, that is equal to minus Q1 by C square minus Me plus MP minus Mn into C square, that is equal to minus 2.4 minus 0.5 plus 938 minus 939.5, that is equal to minus 4.4 MeV. So this is the answer. The next question is, a nucleus decays by the emission of a gamma ray from an excited state of spin parity 2 plus to the ground state with the spin parity 0 minus. What is the type of corresponding radiation? To solve this question, we need to remember this table. That is, for electric dipole, that is E1, L is equal to 1 and parity is S. And for magnetic dipole, that is M1, L is equal to 1, parity no. Electric quadrupole E2, L is equal to 2, parity no. Magnetic quadrupole M2, L is equal to 2, parity yes. Electric octopole E3, L is equal to 3, parity is yes. Magnetic octopole M3, L is equal to 3, parity is no. Electric hexadecapole E4, L is equal to 4 and parity is no. Magnetic hexadecapole M4, L is equal to 4 and parity is yes. So here during this reaction, the J pi values is changing from 2 plus to 0 plus. Here the parity change is no. That means here in the both states the parity is positive. So no change in parity. So that delta pi is equal to no change, that is no. So here the J value of parent nuclei, that is equal to 2 and total nuclei is 0, that is Jp minus Jd less than or equal to L less than or equal to Jp plus Jd, that is 2 minus 0 less than or equal to L less than or equal to 2 plus 0, that is L is equal to 2. So that here L is equal to 2 and there is no change in parity, so that we can say this is the electric quadrupole. So the answer is electric quadrupole. The next question is, the ground state of 12 Pb207 nucleus has spin parity Jp is equal to 1 by 2 minus, where the first excited state Jp is equal to 5 by 2 minus. The electromagnetic radiation emitted when the nucleus makes a transition from the first excited state to the ground state R dash. So here the spin and parity of ground state is given as 1 by 2 minus and the first excited state is given as 5 by 2 minus. So here the L value is 5 by 2 minus 1 by 2 less than or equal to L less than or equal to 5 by 2 plus 1 by 2. That is 2 less than or equal to L less than or equal to 3. That is L is equal to 2 and 3, and as the parity has no change, that is delta pi is equal to 0. That is, if L is equal to 2 and delta pi is equal to no, that is it is the E2. Then for L is equal to 3, delta pi is equal to no, it is M3. The next question is a 60 CO nucleus beta decays from its ground state with Jp is equal to 5 plus to a state of 60 Ni with Jp is equal to 4 plus. From the angular momentum selection rules, the allowed values of orbital angular momentum L and the total spin S of the electron anti-neutrino pair is dash. So here the reaction given is 60 CO gives 60 Ni plus beta plus nu E. That is, here the value of J pi is given as 5 plus and 4 plus. So here the delta J value is plus or minus 1 and delta pi is equal to 0 because here no change in the parity, it is always positive. So here if delta j is equal to plus or minus 1 and delta pi is equal to 0, we can say that it is the allowed Gamow-Teller transition. For Gamow-Teller transition, we know S is equal to 1. So if S is equal to 1 and delta j is taken as 1, we can write j is equal to L plus S implies L is equal to 0. So that here L is equal to 0 and S is equal to 1. So this is the answer. The next question is, consider the decay A gives B plus C of a relativistic spin half particle A. Which of the following statement is true in its stress frame of particle A? So here the reaction given as A gives B plus C, and here the spin of A is given as half. If the spin of B and C is taken as half, then S1 and S2 is taken as half, that is S is equal to S1 plus or minus S2, that is equal to 0 and 1. So if the spin of B and C is taken as half, then the spin is not conserved. That is, the LHS side the spin is half and in RHS spin is 0 and 1. So the spin is not conserved. So that the option A is wrong. Then the sum of the masses of B and C is greater or less than A. It is not mandatory that it is always greater. So the option B is also wrong. Then for option D, if the spin of both B and C become integral, here also the spin is not conserved because if the B and C has the integral value, then here it is given that the spin of A is half, then it doesn't matches. So the LHS and RHS doesn't matches. So option D is also wrong. The correct option is the energy of B is uniquely determined by the masses of particle. This is the correct option. So the answer is C. The next question is, the charm cork has the assigned a charm quantum number C is equal to 1. Then how should the Gelman-Nishijima formula for electric charge be modified for 4 flavors of corks? So this is a theoretical question. We know that Gelman-Nishijima formula is Q is equal to I3 plus half into B plus S. And for cork, it is generalized as Q is equal to I3 plus half into B plus S plus C. So this is the answer. The next question is, a spin half particle A undergoes the decay A gives B plus C plus D, where it is known that B and C are also spin half particles. The complete set of allowed values of the spin of particle D is dash. So here the reaction given is A gives B plus C plus D, and it is given that the spin of A is half and B and C is also half. So here if the spin of B and C is half, then the sum is 0 and 1. Let the spin of D be x. So here we know that the LHS has the spin value half and the RHS spin value is 0 plus 0 or 1 plus x. So if x is equal to half, then the RHS value will be, if B plus C is equal to 0, then the RHS value is equal to 0 minus half to 0 plus half. Then the answer is half. Then the RHS become half and LHS is also half as the spin of A is half. then we know that the spin is conserved. So here the spin is conserved only if the spin of D is, that is, x is equal to half. So the answer is half only. The next question is, a baryon X decays by strong interaction as X gives sigma plus pi minus plus pi 0, where sigma plus is a member of isotriplet. Then the third component I3 of the isospin of X is dash. So here let the reaction be X gives sigma plus plus pi minus plus pi 0. Then take the value of I3. Then the I3 value of sigma plus is 1, pi minus is minus 1, pi 0 is 0. Then the sum becomes 0. So if the I3 value is to be conserved, then the I3 for x is also 0. So here the I3 for x is 0. So 0 is the answer. The next question is, the beam of pions is incident on a proton target, giving rise to the process pi plus plus p gives n plus pi plus pi plus. Assuming that the decay proceeds to strong interactions, the total isospin I and its third component I3 for the decay products are dash. So here we need to find the value of I and I3 for the decay products. That means we need to find the sum of the isospin I and the I3 value of n, pi plus and pi plus. So that we can write the equation that is given here is pi plus plus p gives n plus pi plus plus pi plus. So the I value can be written as 1 half half 1 1. The RHS side gives the value as 5 by 2. That is, the sum of the value of I for the n, pi plus and pi plus is 5 by 2. And for I3 it is 1 half minus half 1 1. The I3 value of the decay products is 3 by 2. That is, the value of I is equal to 5 by 2 and I3 is equal to 3 by 2. So the option C is the correct answer. Next question is, the dominant interactions underlying the following process K minus plus B gives sigma minus plus pi plus. B is mu minus plus bu plus gives K minus plus K plus, and C is sigma plus gives P plus pi 0 R dash. So here the first reaction is K minus plus P gives sigma minus plus pi plus. So here the strangeness value is minus 1 0 minus 1 0. Here S is conserved. Then the value of I3 is minus half half minus 1 1. Here also I3 is conserved. Then for I it is half half 1 1. But here I value is not conserved. As I value is not conserved, it is not a strong interaction. It can be weak or electromagnetic. But for weak interaction, no term is conserved. That is, Si3I is not conserved in weak interaction. The second reaction is mu minus plus mu plus gives K minus plus K plus. The value of I is 0 0 half half. It is not conserved. Then the value of S is 0 0 minus 1 1. It is conserved. Then the value of I3 is 0 0 minus half half. It is also conserved. So we can say that here B is electromagnetic. Moving to the third reaction, that is sigma plus gives P plus pi 0. We can write the strangeness value as minus 1 0 0. The symbol is that strangeness value is not conserved. That is, it is a weak interaction. So here B is electromagnetic, C is weak, and here A can be weak or electromagnetic. The most appropriate answer will be A is electromagnetic, B is electromagnetic, and C is weak. But in the option, it is not given. So the closest correct answer is option D. So we can say A is weak, B is electromagnetic, and C is weak. A can't be considered as a strong interaction as I is not conserved. The next question is consider the four processes, that is P plus gives N plus E plus nu E, pi plus gives E plus nu E, lambda 0 gives P plus E plus nu E, and pi 0 gives gamma plus gamma. Which of the above are forbidden for free particles? So, in the first reaction, that is P gives N plus E plus nu E, it violates the energy conservation because the correct reaction is P plus E gives N plus nu E because it is a electron capture reaction. So the correct reaction is this. So here the given reaction is wrong. So it is a forbidden reaction. Then the second reaction, that is lambda 0 gives P plus E plus nu E. So here the charge is 0 gives 1 plus 0. Here the charge is not conserved. So the second reaction is also forbidden. Then moving to third reaction, that is pi plus gives E plus nu E. Here the charge is 1 1 0. That is charge is conserved here. So here the option, the reaction 3 is allowed. And moving to the fourth reaction, that is pi 0 gives gamma plus gamma. In this reaction, energy and charge is also conserved. So we can say that first and the second reaction is forbidden. So the answer is option D. The next question is consider the following processes involving the free particles. That is N gives P plus E plus nu E, P plus N gives pi minus, and P plus N gives pi plus pi 0 plus pi 0. And P plus nu E bar gives N plus E plus. Which of the following statement is true? So here the reaction given as N bar gives P bar plus E plus nu E bar. These all are antiparticles and the charges are 0, -1, 1 and 0. So we can say that here charge is conserved and the spin is minus half, minus half, minus half, minus half. This is minus half because they are all antiparticles. So here also spin is not conserved. Then electron lepton number, that is Le, that is 0 0 -1 -1. It is also not conserved. So we can say that the first reaction doesn't obey all conservation law. So option A is wrong. Here the second reaction is P plus N gives pi minus. Then here the baryon number is -1 1 and 0. So here B is conserved. And for the third reaction, P plus N gives pi plus pi 0 plus pi 0. Here the baryon number is 1 1 0 0 0. Here the baryon number is not conserved. So it is not strong or weak or electromagnetic interaction. So option C is also wrong. Because as B is not conserved, we cannot say that it is strong, weak, or electromagnetic. So option C is also wrong. The fourth reaction is P plus nu E gives N plus E plus. The baryon numbers are 1 0 1 0. Here B is conserved and the lepton number is 0 -1 0 -1. Here L is also conserved. So the option D is also wrong because option D says that it violates the lepton number conservation. But here L is conserved. So option D is wrong. Then we know that the second reaction is P plus N gives pi minus. We know the mass of P and N is greater than mass of pion. So if the momentum or energy to be conserved, some energy should be released so that it is not conserved here. So that it means it violates the energy and momentum conservation. So the option B is right because option B says that the second reaction is conserves the baryon number and it violates the energy momentum conservation. So the option B is right. The next question is which of the following reactions are allowed by conservation laws, that is pi plus n gives lambda 0 plus k minus and pi minus plus p gives lambda 0 plus k 0. So here the reaction given as pi minus plus n gives lambda 0 plus k plus. So here the Q is 1 plus 0 gives 0 plus 1 and period number is 0 plus 1 gives 1 plus 0 and S is 0 plus 0 gives minus 1 plus 1. So here the reaction is allowed. And in the second reaction, that is pi minus plus p gives lambda 0 plus k 0, that is Q values are minus 1 plus 1 gives 0 plus 0 and b is 0 plus 1 gives 1 plus 0 and s is equal to 0 plus 0 gives minus 1 plus 1. So the reaction is allowed. So the both first and second equation allowed by the conservation law. So the option A is the right answer. Next question is which of the following process is not allowed by the strong interaction but is allowed by the weak interaction. So here we need to check each option. In option A, the reaction given is K0 plus pi 0 gives K0 bar plus pi minus. Here the charges are 0, 0, 0, plus 1, minus 1 respectively. So we can say that here the LHS and RHS is equal, that is charge is conserved. And for spin, it can be written as 0, 0, 0, 0, 0. So it is also conserved. Then the isospin value is half 1, half 1, 1. It is not conserved. And the I3 value is minus 1 by 2, 0, 1 by 2, 1, minus 1. That is I3 is not conserved. Then the value of strangeness, that is plus 1, 0, minus 1, 0, 0. The strangeness value is also not conserved, that is the change in strangeness value, the delta S is equal to 1. So we can say that here this reaction is not allowed by strong interaction but allowed by weak interaction, because here I3 and S is not conserved, so we can say it is not a. The next question is which of the following elementary particle processes does not conserve strangeness? So here the solution is, here the option A says that the reaction is pi 0 plus p gives k plus lambda 0. So we can say that the strangeness value is in the order 0, 0, plus 1, minus 1 respectively. So we can say that here the strangeness value is conserved in this reaction. Then the option B, that is pi minus plus p gives k0 plus lambda 0. Here the strangeness value is 0, 0, 1 and minus 1. Here also it is conserved. Then the third reaction, that is delta 0 gives pi 0 plus n. Here also the strangeness value is 0, 0, 0. So here strangeness value is conserved. Then the next reaction is K0 gives pi plus pi minus. That is the strangeness value is plus 1, 0, 0 respectively. So here the strangeness value is not conserved. So the option is option D is the answer, because D is the only option that doesn't conserve the strangeness value. The next question is the recently discovered Higgs boson at the LHC experiment has a decay mode into a photon and a Z boson if the rest masses of Higgs and Z boson are 125 gigaelectron volt per c square and 90 gigaelectron volt by c square respectively, and the decaying Higgs particles is at rest, the energy of the photon will approximately be dash. So here the Higgs boson gets decays to Z boson and photon. So the energy of the photon can be written as energy of the Higgs boson square minus energy of the Z boson square divided by 2EH. That is equal to, we know E is equal to mc square, that is mh square minus mz square into c square divided by 2mh, that is equal to 125 the whole square minus 90 square divided by 2 into 125. So this is equal to 30.1 gigaelectron volt. So the answer is 30 gigaelectron volt. The next question is, in the Large Hadron Collider, two equal energy proton beams traverse in the opposite direction along a circular path of length 27 km. If the total center of mass energy of a proton-proton pair is 14 TeV, which of the following is the best approximation for the proper time taken by a proton to traverse the entire path? So here two protons is moving in the opposite direction covering a path of circular. So it covers a distance of 2 pi r, which is equal to 27 kilometer. And here the energy of proton-proton pair is 14 TeV. In center of mass frame, both the protons have the same energy. So the energy of one proton is EP is equal to 14 by 2, which is equal to 7 TeV. The rest mass energy of proton is equal to m naught c square. This is equal to 938 MeV. We know energy E is equal to mc square, that is equal to gamma m naught c square. And we can write E is equal to gamma m naught c square, that is 1 by gamma is equal to m naught c square by E, that is equal to 938 MeV by 7 TeV, that is equal to 938 into 10 power 6 divided by 7 into 10 power 12, which is equal to 1.34 into 10 power minus 4. And we know that T naught, which is equal to T into square root over 1 minus V square by C square. T naught is the proper time, that is T naught is equal to T divided by gamma, where gamma is 1 divided by square root over 1 minus V square by C square. We know T is equal to D by C. This is equal to 27 into 10 power 3 divided by 3 into 10 power 8, which is equal to 9 into 10 power minus 5 second. So T naught is equal to 9 into 10 power minus 5 into 1.34 into 10 power minus 4. This is equal to 1.2 into 10 power 8. This is equal to 12 ns. So this is the answer. Next question is, muons are produced through the annihilation of a particle A and its antiparticle, namely the process A plus A bar gives mu plus mu minus. A muon has a rest mass of 105 MeV by C square and its proper lifetime is 2 mus. If the center of mass energy of the collision is 2.1 gigaelectron volt in the laboratory frame that coincides with the center of mass frame, then the fraction of muons that will decay before they reach a detector placed 6 km away from the interaction point is dash. So here we need to find the fraction of muons that will decay before they reach a detector. So we need to find the value of n by n naught. So the reaction given is A plus A bar gives mu plus mu minus. Here the number of the decayed particles is n is equal to n0 e raised to minus lambda t, and we know lambda is equal to 1 by tau, where tau is the time. So we can write n is equal to n0 e raised to minus t by tau. So we know that by the concept of time dilation, tau lab is equal to gamma tau naught. So we can write n is equal to n0 e raised to minus t by gamma tau naught. That is n divided by n naught is equal to e raised to minus t by gamma tau naught. And we know that time is equal to distance by velocity, that is t is equal to d by c. So we can rewrite it as n by n0 is equal to e raised to minus d by c gamma tau 0. And we know that m is equal to gamma m0, that is m0 is the rest mass. So we can rewrite it as 2.1 into 10 power 9 ev by c square is equal to gamma into 105 into 10 power 6 ev by c square, where gamma is equal to 2.1 divided by 105 into 10 power 3, that is 20. So we can write n by n naught is equal to e raised to minus 6 into 10 power 3 divided by 3 into 10 power 8 into 20 into 2 into 10 power minus 6. This is equal to e raised to minus 1 by 2. So this is equal to 0.606. So this can be written as 1 minus e raised to minus 1. So option B is the right answer. The next question is, in a classical model, a scalar spin zero mesons consist of a quark and an antiquark bound by a potential V of R is equal to AR plus B by R, where A is equal to 200 MeV femtometer raised to minus 1 and B is equal to 100 MeV femtometer. If the masses of the quark and antiquark are negligible, then the masses of mesons can be estimated as approximately dash. So here we know that the meson are spin zero particles, and for spin zero particles total energy is equal to potential energy, that is E is equal to V of R. Here E is equal to mc square, where m is equal to E by c square, and V of R is given as AR plus B by R. And for bound state or stable state, dou V by dou R at R equal to R0 is equal to 0, and dou square V by dou R square is greater than 0. Then here dou v by dou r is equal to 0. This gives a minus b by r square is equal to 0. That is r square is equal to b by a, where r is equal to plus or minus square root over b by a. So here dou square v by dou r square is equal to minus 2b by r raised to 3. For a bound state, this should be greater than 0. This will be positive only if b is negative. So here the energy value E is equal to B of R. This is equal to a into square root over b by a plus b into square root over a by b. This is equal to square root over ab plus square root over ab. This is equal to 2 square root over ab. This is equal to 2 into root of 200 into 100. This is equal to 200 root 2 MeV. That is m is equal to E by c square. This is equal to 200 root 2 by c square. That is 200 root 2 divided by 3 into 10 power 8. This is equal to 200 into 1.41 MeV by c square. That is 280 MeV by c square. So this is the answer. Next question is, the range of nuclear force between two nucleons due to the exchange of pion is 1.40 Fermi. If the mass of pion is 140 MeV by c square and the mass of rho meson is 770 MeV by c square, then what is the range of force due to the exchange of rho meson? So here we know that the range of force is proportional to 1 by mass. That is R of RHO by R pi is equal to M pi by M RHO. That is R RHO is equal to R pi into M pi by M RHO. That is equal to 1.40 into 140 divided by 770. This is equal to 0.25 Fermi. So this is the answer. The next question is, the mean lifetime of the following decay: rho 0 gives pi plus plus pi minus, pi 0 gives gamma plus gamma, mu minus gives E minus plus mu E bar plus nu mu, are tau p, tau pi, tau mu respectively. So they satisfy dash. So here we need to understand the characteristic lifetime for different interaction. That is, for strong interaction, it is in the range of, it is less than 10 raised to minus 22 second, and for EM interaction, it is in the range less than 10 raised to minus 14 to 10 raised to minus 21 second, and for weak it is less than 10 raised to minus 13 to 10 power 3 second. So from here we understood that the mean lifetime of strong interaction less than mean lifetime of the electromagnetic interaction less than the mean lifetime of the weak interaction. So here the reaction rho 0 gives pi plus plus pi minus is a strong interaction, and pi 0 gives gamma plus gamma is electromagnetic interaction, and mu minus gives E minus plus mu E minus plus mu nu is a weak interaction. So we know that tau strong is less than tau EM less than tau weak. So we can say tau rho is less than tau pi less than tau mu. The next question is, a particle which is a composite state of three quarks U, D and S has electric charge, spin, strangeness respectively equal to dash. So here the charge of U is plus 2 by 3, D is minus 1 by 3, S is minus 1 by 3. Taking the sum, we get the answer as 0. Then the spin of U, D and S is half. So taking the sum, we can get it as half or 3 by 2. We know that S is equal to S1 plus or minus S2. So in this way, we can get the answer as half or 3 by 2. Then the strangeness value is of D is 0. U is 0 and S is equal to minus 1. So taking the sum, we get the answer as minus 1. So the charge is 0, spin is 1 by 2 or 3 by 2, strangeness is minus 1. So the option C is the right answer. The next question is, the elastic scattering of neutrino nu E by the electron, that is the reaction nu E plus E minus gave nu E plus E minus. can be described by the interaction Hamiltonian. H is equal to 1 by root 2 into gf integral over d cube x into psi e bar of x gamma mu psi of nu e of x psi of nu e bar of x gamma mu psi e of x. The cross section of the above process depends on the center of mass energy E as dash. So here the total cross section is sigma and Gf is the Fermi constant. So when the neutrino is present, then it is a weak interaction. So for weak interaction, we know that sigma is proportional to Gf square, and for EM interaction, sigma of E is proportional to alpha square, where alpha is the fine structure constant. So here the given interaction is weak interaction, that is sigma of E is approximately equal to Gf square into e raised to x. So here we need to find the value of x. In the natural unit system, h cut is equal to c is equal to 1, and the dimension of E is, we know that E is equal to mc square. So here c is equal to 1, so we can write it as m. So the dimension of h cut c is ml, that is equal to a constant, and we know that L is proportional to 1 by m, and Gf square is proportional to cross section area, that is Gf square is proportional to L square. So Gf square is proportional to 1 by m raised to 4. So we can write the equation 1 as sigma is proportional to m raised to minus 2 the whole square into e raised to x, that is L square is proportional to m raised to minus 4 into e raised to x, that is 1 by m square is proportional to m raised to minus 4 into e raised to x. From here we understood that e raised to x is proportional to m square, and we know that the dimension of E, that is equal to m. So we can say that x is equal to 2. So that sigma is proportional to E square. So this is the answer. The next question is the charged pions pi minus decays to muons, mu minus and anti-muon neutrino, nu mu bar. So the reaction is pi minus gives mu minus plus mu nu. Take the rest mass of muon and pion to be 105 and 140 MeV respectively. The probability that the measurement of muon spin along the direction of its momentum is positive is closest to dash. So here the interaction given as pions gives muons and antimuons. So we know that muons and antimuons have the spin angular momentum along their linear momentum. So we need to find the probability. As they both are in the direction of the momentum, we can say that the probability is maximum. That is, it is 1. So the answer is 1. The next question is the Q value of alpha decay of 232 Th to the ground state of 228 Ra is 4082 keV. The maximum possible kinetic energy of alpha particle is closest to dash. So here we know that Q alpha is equal to 4082 keV, and we know that Q alpha is equal to A divided by A minus 4 into K alpha. That is 4082 is equal to 232 divided by 232 minus 4 into K alpha. From here K alpha is equal to 228 by 238 into 4082. This is equal to 4012 kilo electron volt. The next question is, in the reaction P plus N gives P plus K plus X mediated by strong interaction, the baryon number B, the strangeness S, and the third component of isospin I3 of the particle X are respectively dash. So for a strong interaction, the baryon number, the strangeness, and the third component of isospin I3 should be conserved. So we need to find the value of B, S and I3 for X in such a way that it should be conserved. So here the reaction given is P plus N gives P plus K plus X. So here we need to find the value of the baryon number, strangeness number, I3 value of X. So the baryon number of P is 1, N is 1, P is 1 and K plus is 0. So in order to make the reaction conserved, we need to put the value of baryon number of X as 1, so that the baryon number of X is taken as 1. Then for strangeness number of P is 0, N is 0, P is 0 and K plus is plus 1. So to make this conserved, we need to take the value of s of x as minus 1. So the strangeness number of x is minus 1. Then I3. Then I3 value of p is plus half, and for n it is minus half, p it is plus half, and for k plus I3 is equal to plus half. So to make this conserved, we need to put the value of I3 of x as minus 1. So here we can say that the baryon number of x is 1, strangeness number is minus 1, I3 is equal to minus 1. So the option B is the right answer. This is the end of this video. Thanks for watching this channel.